cosine function here, we have sine function here. And the rest of here is only a function of x and function of y, right? The function of y, okay? And I try to using the one circle equation, cosine square plus cosine square of this plus sine square of this equal to what? Like here, this is equal to what? Okay? Right, there's no objection, right? Every is satisfied. Cosine square plus sine square is equal to what? Okay, so I using that, you can see cosine this function here, okay, can be written as x1 divided by this and this, give me this cosine function. And then the sine function here can be written as y1 divided by this and this, right? Can give me the y. And I substitute this cosine and sine function into this equation, I can give you this relationship equal to 1. Okay? And what's this relationship look like? x1 over 2 divided by a constant plus y1 squared divided by a constant equal to 1. What's this equation look like? It looks like an elliptic equation, right? Remember what's elliptic? X squared divided by a squared, right? Plus y squared divided by b squared. Okay? That's an elliptic equation. This is a from here to here is a from here. 对，椭圆方程式。Okay? Our baseline will be what? The elliptic function. Elliptic. This is look like elliptic function. Okay. So give me the You can plot any location. Okay. Y. Give me the attribute. Give me the location y equal to 0. This is y equal to 0. And on the free surface, I can find out the baseline will look like this. This is our baseline. When y equal to here, and I can find my elliptic function because I have a different y height. This is the height, right? Y is a different location, a different height. This elliptic, the axis will be different. Okay, so our trajectory of flow particle is what? Is elliptic function. Elliptic function. Okay, so we can check when y equal to 0. That's on the free surface. This is here. Okay, so y equal to 0. This one, will be reduced to 0, right? And this is a constant because this is not a function of y. This is equal to 1, so become hypercotangent. This is a hypercotangent times epsilon square. This is epsilon square, right? And hypercotangent square. So this is become like this. And on the your y here, hypercosine y equal to 0. This is equal to 1. And this is constant, this is equal to 0, so it becomes 1 here, so it becomes epsilon square. So this is elliptic function for what? On the free surface, that represent the free surface particle should rotate like this. Okay, so on the free surface, as you can see, rotate like this is an elliptic function. Okay, it's a baseline is elliptic. Okay, and then if you consider the baseline here. As you can see, this is y equal to minus h. When you apply this boundary condition into this equation here, you end up with what? You end up with you will degenerate this elliptic will degenerate into this path. This path is just back and forth path. We don't have any y-axis anymore. Let's follow what? Follow the boundary condition, right? Because when you have this, you have the penetration. This is v velocity, and here we're not able to have v velocity because when you have v velocity, you will be penetrate into the surface. That will be violate what? Boundary condition. No flow penetration into the boundary condition. Bottom wall here. So here when you apply y equal to minus h into this solution form, you will end up with x function. This is equal to 0. This is total cancel, and then there will be end up with what? End up with should be x will be changed between two values. Okay, change with these two values. So that will back and forth moving like this. Okay, you can check. Okay, that's the path. Okay, path line for the when you have the flow with the free interface, right? Again, we go back to here. We have this sinusoid interface. What the path line look like? Okay, what the path line look like? It's an elliptic path line like this. Okay. But this elliptic, the axis, longer axis and shorter axis will change with a y location because this is a y. Is a y. For different y, you get a different longitudinal and then transverse or the lateral axis. Okay, the length. Okay, so this length is different. This length is different. And a different y here. Okay, so let's give you the path line for our flow field. Okay, and here, okay, as you can see, this path line equation, if you have this h much greater than lambda, what happens? H much greater than lambda means deep water, right? H is very deep, okay, very deep water. So this approach to 1, because h over lambda is much greater than 1. Let's go to infinity, for example. This will approach to 1. This hypercotangent also approach to 1. So our equation, our path line equation reduced to this. What's this? As you can see, this parameter here and this parameter here is exact the same. When they are exact the same, what happens? It's A and B are exactly the same. What happens? Become what? Become x squared plus y squared equal to a squared. That become circle, right? So if you have a deep, very deep liquid, okay, your path line will change to circle. Okay, change to circle. Okay, that will be the when you have the deep liquid. Okay, for deep liquid, the derivative becomes circle. Okay, so that's information you can get from this analysis here. Okay, next. Standing wave. What's the standing wave? Okay, we're talking about standing. Before this section, we're all talking about traveling wave, right? What's the traveling wave? If you consider this. This is traveling wave. This is traveling wave. This is traveling around the direction, right? The green line here is the traveling wave. The traveling. Okay, if you go back again. And this is another traveling wave. You can see this is another traveling wave, right? This is not, I just follow the traveling wave, but this traveling wave is traveling to the left. This is another traveling wave. The only difference is the traveling wave direction. One is the positive wave speed, right? One is the negative c, one is the positive c. Okay, the speed is just reverse direction. Okay, so that's the traveling wave we're talking about. So before this section, we all consider is what? We only have one traveling wave. Okay, when we have a one traveling wave like this, traveling along the surface, what the flow field look like? Just analysis. Okay, and here we try to understand when we have a standing wave. Okay, and what the standing wave that means? 什么是驻波？驻波，in Chinese we call it 驻波。什么是驻波 definition? Okay. Standing wave in here. Okay, as you can see here. Okay. The yellow line, as you can see this point here. Okay. We should repeat whatever. You can see here. The change is always the amplitude here always equal to 0. This point also, right? This point also. The change. Okay. As you can see, this kind of wave, very spatial. It's not like a traveling wave, right? Traveling wave is always moving into one direction. And this wave is only here is a here is a fixed, here is a fixed, here is a fixed, and only between 2 points here. Okay, between these 2 points here, this point and this point here. Okay, it's moving, right? It's moving upward. Okay, and the other side is moving downward. If you See that? That's a standing wave. Okay, it's called standing wave. The standing wave has very specific so-called node point. Because this is a node. And at this node point, okay, the velocity or the amplitude will be equal to 0. At this node point, amplitude will be equal to 0. The amplitude is equal to 0. Amplitude is equal to 0. It didn't oscillate at all. But away from the node, there's a positive amplitude, negative amplitude change, right? But on the node point, okay, on this node point, we don't have any amplitude. All these points are node point. Okay? So when we have a node in a wave, we call this is a standing wave. Okay? And how to compose a standing wave? 怎么样 standing wave 怎么样形成的？怎么样可以把它一个 standing wave 把它组合起来 ？We can have this, okay? We can have this two traveling wave, one travel to the right, one travel to the left. When we supercompose one travel to the left and then they will get this standing wave. Okay, if you can see that. So I can superimpose one is a traveling wave A.1, the other is traveling wave A.2. The A.1, A.2 is the difference is what? One traveling to the right, one traveling to the left. So this is minus C here, it's a positive C here. Okay? And amplitude only one half of each node, for example. And I can superimpose these two. As you can see, this standing wave is equal to A.1 plus A.2. So this is A.1, this is A.2. Okay, and then I using the sine alpha plus beta give me what? Sine cosine minus cosine sine, right? So this is 2 pi x minus cosine 2 pi over lambda ct, right? Minus cosine of this times sine of this, right? That's it. I can using the formula just, okay. So this is from this formula here. This formula here I can have this, okay. And then so this is the first one here, I can have this. And the second one here, I can have this. And when you consider this and this, they can be cancelled. Because this is cosine sine. Argument is exactly the same. But this is minus sine, this is positive sine. These two should be cancelled. So only these two terms can be left, right? So this cosine, sine cosine, plus sine cosine, right? And become 2 times 1 half become each node. So each node of this, that's a standing wave. Okay, the standing wave. So this is become the standing wave. Okay, so standing wave, the A dot can be written as A dot sine 2 pi x over lambda cosine 2 pi ct over lambda. Okay. Okay, that's a standing wave. Okay. And usually we can have the so-called frequency. Frequency can be divided F equal to C over lambda. And angular frequency is omega. Omega is 2 pi over lambda. If you're using that, okay, this C over lambda can be written by F to become 2 pi Ft. Okay, 2 pi Ft here. And 2 pi Ft become omega because 2 pi over lambda, okay. 2 pi Ft, okay, 2 pi Ft is our 2 pi C over lambda, yeah, just 2 pi F, so C over lambda is our F, so 2 pi F is our omega, right, so cosine omega T, so this is angular frequency, okay, F is our frequency for this wave. Sometimes we written like this. Okay, so this is how do we compose of the standing wave by using the two traveling wave, one travel to the left, one travel to the right, and then superimpose together. Okay, you can get this function, and this function gives us at a certain x, as you can see, a certain x. If this number equal to 0, that's the sign of this x location equal to 0. That means there is no amplitude. That's our node, right? That's our node. Okay. So this is x, right? This is x. So x equal to certain number here, and this sine function equal to 0. That give me, okay? Give me this amplitude is equal to 0. The amplitude equal to 0, that's a null point. Okay, that's our note. Okay, and how do you write down the standing wave flow? When I have a standing wave, okay, when I have this standing wave here, what the flow here underneath look like? Should we do again, or because right now we change our service become from the traveling wave, right? This is traveling wave, become standing wave. Can we write our Kaplan equation and then try to deliver everything again? We don't need to do that. Because remember, what? Potential flow is a linear equation. Linear equation, they can superimpose two solutions. These two solutions can be represented one solution for this traveling wave, one solution for this traveling wave, and I superimpose these two solutions will be the standing wave solution. This standing wave solution also the solution for our Laplace equation. Remember that, right? Okay. So we don't have to do again. Okay. Once we have the traveling wave solution, and only the traveling wave is minus c, 1 is positive c, I can immediately compose new solution for the standing wave. Okay, here is our what? This is our complete potential what? For traveling wave. From here, this is our complete potential for traveling wave. And this is with the amplitude epsilon, right? And I will superimpose one to the left, one to the right. And so what should I change? The standing wave will look like this, and this will be cosine, right? Z minus CT here, right? Z minus CT. Epsilon here, I only have 1/2, right? This is a travel to the right. And another one is here, right? This function, this is also 1/2 of this, right? And this Z minus CT becomes Z plus CT. So of this, superimpose these two together. This new complete potential is solution for what? It's our standing wave solution. Beautiful. We don't have to do again. Okay, fortunately. Otherwise, I will run out of my time. Okay. So how powerful this kind of the phenomenon, this kind of technique. Okay, once you know the basic flow, you can generate another new flow field. So this is a standing wave complete potential. Okay, can you follow me? Okay, anyway, by using this, you can also simplify. Okay, you can simplify by this. You can simplify this and become like this, and you can even simplify your complete potential become like this later. Okay, but I don't think it's too much difficulty. Okay, because this is cosine alpha plus beta become cosine sine, right? And this is a cosine again, alpha plus beta become cosine sine. So just alpha beta just change. Okay, try to find out what is alpha, what's the beta. This is alpha, this is beta. Okay, this is alpha, this is beta. Okay. So this is an equation we will use cosine. Okay, cosine plus sine, cosine minus sine. Give you this. Okay, so this is a cosine alpha plus beta. Okay, or alpha minus beta. Okay, you can have this, and you can cancel one of that and simplify our complete potential for standing wave. Okay, with a lambda. So this is the complete potential. Okay, I think I run out of time. Okay, I don't think I would like to go further. Okay, so next we would like to try to find the path line for the standing wave. So I will leave to on Thursday. Okay, so Thursday we have a start from 1 o'clock. Okay, remember instead of 2. Okay, we will start from 1 o'clock. So we will try to finish this.